Hello, welcome back, my friends. Here's the code I just write according to the original code at the book we are reading. And from this typing, I got a better understanding about what is neural network. It's all about the weights and the input, output, and also the error. Okay, now let's go to the chapter 7, how to picture neural networks in your head and on paper. In this chapter, we will learn correlation summarization, simplified visualization, seeing the network predict, visualizing using letters instead of pictures, linking variables, the importance of visualization tools. Numbers have an important story to tell. They rely on you to give them a clear and convincing voice. It's time to simplify. It's impractical to think about everything all the time. Mental tools can help. Chapter 6 finished with a code example that was quite impressive. Just the neural network contained 5 lines of incredibly dense code. Reading through it, it's clear there's a lot going on, and that code includes over 100 pages of concepts that, when combined, can predict whether it's safe to cross the street. I hope you are continuing to rebuild these examples from memory in each chapter. As the examples get large, this exercise becomes less about memorizing specific letters of code and more about remembering concepts and then rebuilding the code based on those concepts. In this chapter, this construction of efficient concepts in your mind is exactly what I want to talk about. Even though it's not an architecture or experiment, it's perhaps the most important value I can give you. In this case, I want to show how I summarize all the later lessons in an efficient way in my mind so that I can do things like build new architectures, debug experiments, and use an architecture on new problems and new datasets. Let's start by reviewing the concepts you have learned so far. This book begins with small lessons and then build layers of abstraction on top of them. We begin by talking about the ideas behind machine learning in general. Then we progressed to how individual linear nodes or neurons learn, followed by horizontal groups of neurons, layers, and then vertical groups, stacks of layers. Along the way, we discussed how learning is actually just reducing error to zero, and we used calculus to discover how to change each weight in the network to help move the arrow in the direction of zero. Next, we discussed how neural networks search for and sometimes create correlation between the input and output datasets. This last idea allowed us to overlook the previous lessons on how individual neurons behaved because it consciously summarizes the previous lesson. The sum total of the neurons, gradients, stacks of layers, and so on led to a single idea. Neural networks find and create correlation. Holding onto this idea of correlation instead of the previous smaller ideas is important to deep learning. Otherwise, it would be easy to become overwhelmed with the complexity of neural networks. Let's create a name for this idea, the correlation summarization. Correlation summarization. This is the key to seemingly moving forward to more advanced neural networks. Correlation summarization. Neural networks seek to to find direct and indirect correlation between an input layer and an output layer, which are determined by the input and output datasets, respectively. At the 10,000 foot level, this is what all neural networks do, given that a neural network is really just a series of matrices connected by layers. Let's zoom in slightly and consider what any particular weight matrix is doing. Local correlation summarization. Any given set of weights optimizes to learn how to correlate its input layer with what the output layer says it should be. When you have only two layers, input and output, the weight matrix knows what the output layer says it should be based on the output dataset. It looks for correlation between the input and output datasets because they are captured in the input and output layers. But this becomes more nuanced when you have multiple layers, remember? Global correlation summarization. What an earlier layer says it should be can be determined by taking what a later layer says it should be and multiplying it by the weights in between them. This way, later layers can tell earlier layers what kind of signal they need to ultimately find correlation with the output. This cross-communication is called backpropagation. When global correlation teaches each layer what it should be, local correlation can optimize weights locally. When a neural in the final layer says, I need to be a slide higher, it then processes to tell all the neurons in the layer immediately preceding it, hey, previous layer, send me higher signal or higher value. Then they then tell the neurons preceding them, hey, send us higher signal. It's like a giant game of telephone. At the end of the game, every layer knows which of its neurons need to be higher or lower, and the local correlation summarization takes over, updating the weights accordingly. The previously overcomplicated visualization. While simplifying the mental picture, let's simplify visualization as well. At this point, I expect the visualization of neural networks in your head is something like the picture shown here because what's the one we used? The input dataset is in layer 0, connected by a weight matrix, a bunch of lines to layer 1, and so on. This was a useful tool to learn the basics of how collections of weights and layers become together to learn a function. But moving forward, this picture has too much detail. Given the correlation summarization, you already know you no longer need to worry about how individual weights are updated. Later layers already know how to communicate to earlier layers and tell them, hey, I need higher signal, or hey, I need lower signal. Truth be told, you don't really care about the weight values anymore, only that they are behaving as they should, properly capturing correlation in the way that generalizes. To reflect this change, let's update the visualization on paper. We'll also do a few other things that will make sense later. As you know, the neural networks is a series of weight matrices. When you are using the network, you also end up creating vectors corresponding to each layer. In this figure, the weight matrices are the lengths going from node to node. Okay, before we read that text, let's just have a look at this graph. Here comes the layer 2, the layer 1, and the layer 0. I believe the layer 0 is the input layer and the layer 2 is the output layer because it only got one node there. But the input layer got 3 nodes in it. Each of them represent red, blue, or and green light. And between each layer, we got its individual weights. The weights 0, 1 represent the weights between layer 0 and layer 1. The weights 1, 2 represents the weights between layer 1 and layer 2. Okay, now it's more reasonable for us to understand, because now we know the weights it is between the two layers. In this figure, the weight matrix are the lines going from node to node, and the vectors are the straps of nodes. For example, weights 1, 2 in a matrix, weights 0, 1 is a matrix, and layer 1 is a vector. Okay, layer 1 is a vector. Every layer is a vector. Good. In later chapters, we will arrange vectors and matrices in increasingly creative ways. So instead of all this detail showing each node connected by each weight, which gets hard to read if we have, say, 500 nodes in layer 1, let's instead think in general terms. Let's think of them as vectors and matrices of arbitrary size. Okay. My life is a joke, but that's okay because we got a joker still inside of me. The simplified visualization. Neural networks are like Lego bricks, and each brick is a vector or matrix. Moving forward, we will build new neural network architectures in the same way people build new structures with LEGO pieces. The great thing about the correlation summarization is that all the bits and pieces that lead to it, backpropagation, gradient descent, alpha, dropout, mini batching, and so on, don't depend on particular configuration of the LEGO's Legos. No matter how you piece together the series of matrices, gluing them together with layers, the neural network will try to learn the pattern in the data by modifying the weights between wherever you put the input layer and the output layer. To reflect this, we will build all the neural networks with the pieces shown out right. The strap is a vector, the box is a matrix, and the circles are individual weights. Note that the box can be viewed as a vector of vectors, horizontally or vertically. Here's a vector, and here's a matrix. It's all numbers, but with different shape. The layer 2, layer 1, layer 0. The big takeaway: the picture at the left still gives you all the information you need to build a neural network. You know the shapes and the sizes of all the layers and matrices. The detail from before isn't necessary when you know the correlation, summarization, and everything that went into it. But we aren't finished. We can simplify even further. The dimensionality of the matrices is determined by the layers. In the previous section, you may have noticed a pattern. Each matrix dimensionality, numbers of rows and columns, has a direct relationship to the dimensionality of the layers before and after them. Thus, we can simplify the visualization even further. Consider the visualization shown at right. We still have all the information needed to build a neural network. We can infer that weights between layer 0 and layer 1 is a 3 times 4 matrices, because the previous layer has 3 dimensions, and the next layer, layer 1, has 4 dimensions. Alright, thus in order for the matrix to be big enough to have a single weight connecting each node in layer 0 to each node in layer 1, it must be a 3 times 4 matrix. Okay, 3 rows, 4 columns. Why it has that shape? It is simply because the previous layer has 3 elements and the next layer has 4 elements or 4 nodes. The only way to collect them individually together is to use a 3 times 4 matrix. Good. This allows us to start thinking about the neural networks using the correlation summarization. All this neural network will to do is adjust the weights to find correlation between layer 0 and layer 2. It will do this using all the methods mentioned so far in this book, but the different configurations of weights and layers between the input and output layers have a strong impact on whether the network is successful in building or in finding correlation. The particular configuration of layers and weights in a neural network is called its architecture, and we will spend the majority of the rest of this book discussing the pros and cons of various architectures. As a correlation summarization reminds us, the neural network adjusts weights to find correlation between the input and output layers, sometimes even inventing correlation in the hidden layers. Different architectures channel signal to make correlation easier to discover. Good neural architectures channel signal so that correlation is easy to discover. Great architectures also filter noise to help prevent overfitting. Much of the research into neural networks is about finding new architectures that can find correlation faster and generalize better to unseen data. We'll spend the vast majority of the rest of this book discussing new architectures. Let's say this network predicts. Let's picture data from the straight line example flowing through the system. In Figure 1, a single data point from the straight line dataset is selected. Layer 0 is set to the correct values. It's a layer 0, 1, 0, 1. It got some value of 1, 0, 1. In Figure 2, 4 different weighted sums of layer 0 are performed. The 4 weighted sums are performed by weight 0, 1. As a reminder, this process is called a vector matrix multiplication. These 4 values are deposited into the 4 positions of layer 1 and passed through the ReLU function, setting negative values to 0. To be clear, the third value from the left in layer 1 would have been negative, but the ReLU function sets it to 0. Okay, in this figure we can say by using the matrix multiplication function, after we did that calculation, we get a series of numbers, and those numbers should go through the ReLU function. So at here, the third position, it should be negative, but after going through the ReLU function, it becomes 0. As shown in Figure 3, final step performs a weighted average of layer 1. Again, using the vector matrix multiplication process, this yields the number 0.9, which is the network's final prediction. Review vector matrix multiplication. Vector matrix multiplication performs multiple weighted sums of a vector. The matrix must have the same number of rows as the vector has values, so that each column in the matrix performs a unique weighted sum. Thus, if the matrix has 4 columns, 4 weighted sums will be generated. The weightings of each sum are performed depending on the values of the matrix. Visualization. using letters instead of pictures. All these pictures and detailed explanations are actually a simple piece of algebra. Just as we defined the simpler pictures for the matrix and the vector, we can perform the same visualization in the form of letters. How do you visualize a matrix using math? Pick a capital letter. I try to pick one that's easy to remember, such as W for weights, and the letter 0 means it's probably one of several W's. In this case, the network has 2. Perhaps, surprisingly, I could have picked any capital letter. The letter 0 is an extra that lets me call all my weight matrix W, so I can tear them apart. It's your visualization. Make it easy to remember. The W means matrix, the L means vector or less. How do you visualize a vector using math? Pick a lowercase letter. Why did I choose the letter L? Well, because I have a bunch of vectors that are layers. I thought L would be easy to remember. Okay, the W means weights, the L means layer. Okay, I could accept that. It's quite simple. I thought L would be easy to remember. Why did I choose to call it L0? Because I have multiple layers. It seems nice to make all them LS and number them instead of having to think of new letters for every layer. There's no wrong answer here. If that's how to visualize matrix and vectors in math, what do all the pieces in the network look like? At the right, you can see a nice selection of variables pointing to the respective sections of the neural network, but defining them doesn't show how they relate. Let's combine the variables with vector matrix multiplication. Linking the variables, the latter can be combined to indicate functions and operations. Vector matrix multiplication is simple. To visualize that 2 letters are being multiplied by each other, put them next to each other. For example, the algebra L0 times W0, it means layers times the weights. The translation of that algebra symbols is take the layer 0 vector and perform vector matrix multiplication with the weight matrix 0. Okay, from here you can see why I just doesn't like the math. Some people love it because it's much you can use less letters to represent a lot of stuff, but I don't like it. Why? Because it's not understandable for normal people like me. But for the translation part, it is different. Anyone that could be able to understand the English, they could understand the theory, any theory about anything. The L1 W1 means take the layer 1 vector and perform vector matrix multiplication with the weight matrix 1. You can even do in algebraic functions like ReLU using notation that looks almost exactly like the Python code. This is crazy intuitive stuff. The L1 means the layer 1 equal to ReLU, so what kind of input we would give to the ReLU function? It is the layer 0 times the weight 0. To create the layer 1 vector, take the layer 0 vector and perform vector matrix multiplication with the weight matrix 0. Then perform the ReLU function on the input, I guess, not the output. Setting on the output, setting all negative numbers to 0. L2 equal to L1 times W1. To create the layer 2 vector, take the layer 1 vector and perform vector matrix multiplication with the weight matrix 1. If you notice, the layer 2 algebra contains layer 1 as an input variable. This means you can represent the entire neural network in one expression by chain them together. Something like this, the layer 2 equal to ReLU LZ WZ Okay, it's quite simple, but you have to read it in a different way. Let's say, thus, all the logic in the forward propagation step can be contained in this one formula. Note, backed into this formula is the assumption that the vectors and matrix have the right dimensions. Okay, that's cool. So how do you get the layer 2? It is simple. First, we will try to calculate the multiplication. We have to do multiplication based on the layer 0 and weight 0. Then we give it to a activation function, and we have to do another multiplication to the W1. That's how we get the layer 2. Everything side by side. Let's say the visualization, algebra formula, and Python code in one place. I don't think much dialogue is necessary on this page. Take a minute and look at each piece of forward propagation through these 4 different ways of seeing it. It's my hope that you will truly grasp forward propagation and understand the architecture by seeing it from different perspectives, all in one place. Okay, that's how to learn new stuff. You have to see that stuff in different respective use in different languages. That's the best way to learn a thing, I guess. And the other knows it, so that's why he did his best to give us a view about the neural network or the deep learning. First, let's say the Python code. Layer 2 equal to ReLU, the layer 0 dot width 0,1, the weights between layer 0 and layer 1. And after that, we do another dot function or dot operation. That's it. And here's the algebra representation of the 0. It's probably the same. It is the same as we seen in the Python code. And here's the graph representation, the inputs, the hiddens, layers, and the prediction. And here's another representation. It is all the same. As I hope you could understand this. The importance of visualization tools. We're going to be studying new architectures. In the following chapters, we will be taking these vectors and matrices and combining them in some creative ways. My ability to describe each architecture for you is entirely dependent on or having a manually agreed on language for describing them. Thus, please don't move beyond this chapter until you can clearly see how forward propagation multiplies these vectors and matrices, and how these various forms of describing them are articulated. Key takeaway: good neural architectures channel signals so that correlation is easy to discover. Great architectures also filter noise to help prevent overfitting. As mentioned previously, a neural architecture controls how signal flows to a network. How you create these architectures will affect the ways in which the network can detect correlation. You'll find that you want to create architectures that maximize the network's ability to focus on the areas where meaningful correlation exists, and minimize the network's ability to focus on the areas that contain noise. But different datasets and domains have different architectures, have different characteristics. For example, image data has different kinds of signal and noise than the text data. Even though neural networks can be used in many situations, different architectures will be better suited to different problems because of their ability to locate certain types of correlations. So for the next few chapters, we will explore how to modify neural networks to specifically find the correlation you are looking for. See you there. So after that, it's a new chapter. We won't discuss that in this video, and I will see you in the next one. Bye.